Hello and welcome everyone to the physics class. And this is circular dynamics lecture number 9. Circular dynamics lecture number 9. And can we recollect what we had done in the previous class? What we were doing in the previous class? Can anyone tell me? What was the point of discussion? What were we
Motion
discussing?
in a horizontal circle.
Motion in a horizontal circle, yes, but
Yes, sir,
what
we have done two problems also.
we have done two problems. Can you remind me what the two problems were about?
Death well, sir. And also a motorcycle riding in a circular vertical wall of radius r. Those
Okay,
two problems.
so we were dealing with problems on the horizontal circle, and very specifically we were dealing with something known as the dead circle. A motorcycle is moving in the cylindrical or conical truncated cone, while a structure and a man sticking himself to the cylinder wall and the floor falling, and will he survive or not? Well, let us move ahead and we'll try to wind up horizontal circular motion in today's class. To begin today's class, let us again start with a similar sort of a problem. As that well, in that well, the cylinder was rotating and the man was lying like this, and the floor went away. He did not fall because of friction between the cylinder and the person. Now, let us get our attention into a problem where similar thing is happening, and if you are able to analyze it and give me an answer to this one, it would be a very good thing. So now the question is like this, and I must tell you that there is no diagram given with the question. So the question goes like this: a hemispherical bowl, the form of a hemispherical shell. It is not a hemisphere. I mean, sometimes the language is a bit confusing. A hemispherical, which means half of a sphere. Sphere is solid, so nothing can go inside it. So this is more of a hemispherical shell. So it's like a shell of a football. Inside it is air, outside it is only a shell. So hemispherical bowl, I should say, a hemispherical shell ball of radius r is rotating about its axis of symmetry. So it is rotating like this, which is kept vertical. So the ball, half football, is kept vertical and it is rotating. Dum, 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 dum. A small ball is kept in the bowl, rotates with the bowl without slipping on its smooth surface. Remember, the surface is smooth, but the ball is not slipping. Wow. And the angle made by the radius through the ball with the vertical is alpha. So if I make the angle between where the ball is with the vertical, the angle is alpha. Find the angular speed at which the ball is rotating. I hope everyone understands the question. There is no diagram given with the question, so you have to think about the diagram. That is the first task. You only get one chance to read the question, remember that, because in the examination hall, you cannot read the same question two times. That is crime, that is sin. We should not commit sin in the examination hall. The question is there in front of you. I'm expecting answers. I hope you will try the question. I'll give you a minute. Think about it, and then I'll be back. Let's see who gives me. Again, answer doesn't matter. Even without doing anything, if you look at the options, you will probably give me the answer. But that is not the way I teach. I don't give you the options with the question. I don't do question with an option because sometimes you get carried away with the option, and sometimes you look at the option and you somehow know that this option is there. Sometimes you even don't know anything, but you will tell me the right option, and that will give you a false sense of achievement. And I don't want that. I want you to think. That's why I hardly do questions which are objective type. I want you to think and get me the answer, and not look at the answer and tell me that this looks like an answer and this will be the answer. I'll tell you all those tricks how to look at the answer and tell me which is the answer. But those are tricks. It may work sometimes, it may not work sometimes. I want you to work on this. Think about it. Tell me how you're going to do it. You have a minute to win it. I hope you utilize the minute and everyone works on the problem. Okay, then what I'll do is I'll give you a hint of how this problem has to be solved, and how I'm going to give you the hint. I will probably show you the diagram, the diagram that you should have drawn with all the forces on the diagram, and that would be my first hint. Hint number one is a diagram that has to be drawn, and the diagram looks like this: hemispherical shell, half football, rotating with an angular velocity omega. As you can see, A is the center of this ball. No, A is not the center of the ball. The center of the ball is O, right at the top. Then you have the small bead of mass M, as you can see. Then you have the radius R of the hemispherical bowl, capital R here. And then you have the small r. The small r happens to be the, see, it is rotating in a horizontal circle. Dung, 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 dung. The small r is the radius of the circle on which this bead is rotating, and this is the value of alpha, the angle that this ball makes with the vertical. Now what you have to find out, what is given to you is the weight of the block, mass mg, mass is m into g, and you are given alpha, and you are given the value of r. So r is known, alpha is known, so I'll just mark the things which are known. R is known, alpha is known, m is known. You have to find out the square value. The square or a rectangle value is omega. You have to calculate the value of omega from these known quantities. I hope everyone has drawn the diagram, and I will expand it so that you can have a closer look. This is the diagram, and now I am expecting some answers. I hope answers are on the way. At least the method of solving it must be known to you. I'll again give you a minute to think about it.
Sir,
Yes, bacha.
I have got omega is equal to under root g cos theta by r.
Under root g cos theta by r. G cos theta by r. G is okay. Dimensionally, is it correct? First of all, that we have to think about this. I think dimensionally it is correct. G by r cos theta. It has to be root of g by r cos theta. If it has to be correct dimensionally. Did you get g by r cos theta, or did you get
root g
yes?
by r cos
If you got root g by r cos theta, well done. If you have done it, root over g by r cos theta is the answer. Well done, bacha. Very well done. Anyone else with the answer? Good job. What's your name, bacha?
Yashwant sir.
Yes, beta. Yashwant. Yes, Yashwant. It's hard to recognize someone from his voice. Becomes very difficult for me to recognize you from your voices. But yeah, I'll try. I'll try to do better next time. Answer is definitely omega is G by R cos alpha or cos theta, whatever you call that angle. That is the correct answer. Well done. I'll give everyone a minute again to work it out. Else, after a minute, Yashwant will guide us in how he has solved the problem. And remember, the answer is not important. The way in which you solve it, that is the most important aspect. You may have used the same method which Ashwant has used. You may not have got the same answer. That means there might be some problem there, some calculation mistakes there. You might have used a different method to get to the same answer.
Yes, sir.
That method is correct. Voila. If your method is wrong, which has some flaw, I should not say wrong, which has some flaw, I will point out that flaw. I'll give you a minute, think about it, and then we will go about and solve this problem. A minute, 2 minutes. Welcome back, everyone. And I hope all of you have tried this question. Now let us go about and solve this. And Yashwant, are you online? Are you there with me?
Yes, sir.
Okay. Please help me in solving this question. How have you solved it? Tell me what is the first step.
Resolve the forces, sir.
Yes, the first is draw the diagram. So the diagram is already drawn there thanks to the notes. With figure ball, everything known to you. Then you have to draw all the forces. Rishwan, what are the forces acting on this small ball? You can see this small ball here. What is the forces acting on this small ball?
G.
One is mg, as you can all see, it is always vertically downwards in the vertical direction. Yes, the other one is
In perpendicular.
n. N, the normal reaction. N, the normal reaction. Remember, it is always perpendicular to whatever surface it is kept on. If it is kept on an inclined plane, like this, then the normal will be like this. If the inclined plane is like this, the normal would be like this. If inclined plane is like this, which is the case here, curved, then it will be like this. In the perpendicular direction, everyone can see this.
Along smaller mg cos theta.
Yeah. In the perpendicular direction, n is in the perpendicular direction. Now it is going in a direction which is like this. We have to resolve it. How do we resolve this? We will resolve it into this component one, the blue one, the red one, and the other component, the green one. Now, how much is this green component? How much is this red component?
mg sin theta, sir.
The green component is mg. Where does mg come? We are talking about n beta, not we are talking about n.
N sin theta, sir. N sin theta.
It has to be n sin theta. How did you get it? Or it should be n cos theta. The green one I'm talking, not the red one. I'm talking about the green one.
Sin theta, sir.
It is not n sin theta. It is n cos theta, bacha. See, this angle is alpha. So this angle has to be alpha. I hope you all understand this. I will enhance the view. I will make the ball bigger so that all of us are able to understand this. I hope now you can see the ball as big as possible. So the green one, this angle is alpha, as you can all see. Then the other angle would be alpha. This angle would be alpha. Do you all understand this? Yes or no? Can I have some raise hand that we understand this? Alternate angle. So this angle is alpha. So this green component becomes n cos of alpha. The green component becomes n cos of alpha. If the green component becomes n cos of alpha, what does the red component become? Anyone? The red component. Yes, the red component becomes n sine alpha. Well done. That is the first way. Now you have to make equations. The first equation that we are going to make is in the tangential direction ft. Tangential direction is the direction in which this ball is rotating. Now remember, it's a smooth surface. Is there any force in the tangential direction on this ball, on this small ball?
0, sir.
0. So we don't have to make this equation at all. There is no equation possible, no force. We leave it as it is. Then we come on to the second direction. Oh, I should not make it in the green. I should make it in the red. I was making a mistake. I'm very particular about colors. Now I make the second equation, which is the equation in the radial direction. Radial direction, centripetal direction, F centripetal.
Omega square R, sir.
F centripetal is m mass into omega angular velocity square into r. Now, which r should I use? There are two r's. Capital R, which is the radius of the hemispherical ball. Small r, which is the radius of the circle, which is the distance between this block to this. This is small r. I hope everyone understands that this is small r. Which r should I use? The small r or the capital R? You have to think about the radius of the circle this small ball is making. How much is the
Capital R,
radius
sir.
of capital R or small r?
Capital R, sir.
No, it is not capital R, bacha. It is small r. The radius of this ball is small r. The circle which the ball is completing is small r. It is not capital R. I hope everyone understands this. Can I have some raise hand that we understand this? The radius of the circle this ball is completing is not this radius. It cannot be this radius. See, this is the center of the hemispherical bowl, and this ball is moving like this. Dang 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 dang. The center is here. The center is here. This is the radius. This is exactly same as your conical pendulum. In the conical pendulum, the length of the string is L, and the ball moves like this. We don't call this L as the length of the radius. It is not the radius. The radius is this part. I hope all of you remember this. This is a type of conical pendulum only, bacha. The only thing is there is no string. Instead of the string, you have a hemispherical bowl. The radius of the hemispherical bowl is capital R. Think about it as conical pendulum. This capital R is actually L, the length of the conical pendulum. Do we all understand this? Can I have some raise hand that we understand this? Okay. So the third equation which we have to make will be in the perpendicular direction. In the perpendicular direction, net force has to be 0. We all understand this. Net force has to be 0. That means the upward and the downward force must balance each other. That means I have an equation. Can anyone tell me what is the equation in the green direction? What is the equation in the green direction? The perpendicular direction.
Is equal to mg, sir.
N cos alpha is equal to mg. That is the equation in the green direction. But now let us come back to the red direction. F centripetal is m omega squared r. Now who is giving this centripetal force? Who is giving this centripetal force?
Alpha, sir.
N sine alpha is giving me the centripetal force. Yes or no?
Yes, sir.
Well done. Now what do? I have n sine alpha here. I have n cos alpha here. If I divide these equations, I can find out the value of omega. Now, but before going into that, I must remember that this small r, we don't know the value of this small r. We only know the value of capital R. We don't know the value of small r. We know the value of capital R. So somehow we need to change. Somehow we need to change from small r to capital R. That means we have to find the value of small r in terms of capital R. How do we do this? Can anyone tell me how do we find out the value of small r from capital R? Small r from capital R. Can anyone tell me how to do this? Small r from capital R. How do we do this? This is my capital R.
Cos theta is equal to small r, sir.
This is alpha and this is small r. Who will tell me the relation between capital R, small r and alpha? And I will not spend much time on this. Small r will be equal to capital R sine alpha. It is not cos alpha. It is sine alpha. I leave it to you to figure it out. This is simple, plain trigonometry of 9th standard. So small r will be capital R sine alpha. I will put this value of small r here. I will put it as capital R sine alpha. Now, if I put it as capital R sine alpha, how does the red equation look like? Can anyone tell me what would the red equation look like? What would the red equation look like? It would look like, oops, why I'm writing n? I don't know why I'm writing n. Okay, it will look like m omega squared into r, capital R now,
is equal to n, sir.
Is equal to n. Well done. That is my first equation. Let me call this as equation number 2 because it is coming from formula number 2. Then the second equation, then the third equation that I've got is the green one. Let me go on to the green equation. Green equation says that mg equates n cos alpha. From here, you have to calculate the value of omega, and I will not go any further from here because if you can't solve this equation, I can't help you. So after getting to equation number 2 and equation number 3, you should be able to get me or yourself the value of omega,
Sir.
and the value of omega you will get from there would be simply how much?
Omega is equal to under root g by cos alpha r, sir.
Yes, solving. So I have come to here because there is no space left there.
Dividing equation 2 and 3, sir.
Yes, but from equation 2 and 3, I can get the value of omega as under root of g by r cos alpha. If you have got this answer in the same way that I have done this problem without any mistakes, congratulations. You have done an excellent job. How many of you have done this problem in exactly the same way? I can see some hands coming from the back benches. No, no one. No one could do this. Jashwant, did we do it in the same way?
Yes, sir.
Congratulations. If you have done it in the same way.
One mistake I have done, sir.
What mistake, bacha?
Smaller, I haven't taken capital R, sir.
So if you have not taken small r as capital R, I mean, if you've taken capital R in place of small r, your answer cannot come same. Then you have done second mistake that instead of n sine alpha, you have written it as n.
Yes, sir.
So you have done two mistakes, but two mistakes done, those two mistakes cancel out each other and you get the right answer. Remember your mistakes. Remember why you got the right answer, because you made similar mistakes at the same on the other side. Whatever mistake you made on the left hand side, the same mistake you made on the right hand side, both the mistakes got cancelled, and that is why your answer was correct. And again, correct answers don't matter. What matters is you are doing the problem correctly. The radius of the circular path which this ball is following is small r, not capital R. Small r is n. Small r is capital R sine alpha, and the centripetal force is n sine alpha and not n. But then sine alpha and sine alpha, both sides will get cancelled. and you get m omega square capital R as n. I will give you a minute to note down this problem, and I'll be back in 1 minute. Well, I hope all of you have noted down the solution. It is very simple. We again have repeated the same steps, following the same steps, making the three equations, then using simple common sense, simple trigonometry, we have achieved the answer. Shall we move ahead in life now?
Sir,
Yes, bacha?
I have a small doubt, sir. Sir,
Yes.
can you re-explain again what is R? Capital R.
Capital R is the radius of the bowl that was given to you. Small r is the radius of the circle this ball is making. Capital R is the radius of the ball.
Okay, sir. Okay, sir. Clear, sir.
Okay. Capital R was given to you. Radius of the ball. Here. You can see capital R, radius of the ball. Small r, radius of the circle this body is making. It is not the radius of the ball. Okay. On that note, let us move on to the last topic of this horizontal circular motion. And any idea what this last topic is all about? The last topic that we are going to do in this horizontal circular motion will be captioned like this: turning of vehicles, cars on circular tracks or circular roads. How does a car, or for that matter a bike, a truck, a bus, turns on a circular road? This is what we have to do in this. It is simple. You have a steering wheel in a car or a bus or a truck. You have a steering handle on a bike. Just turn the handle, you turn. What is there to understand? Where is this physics here? Yes, beta?
Racing tracks, sir.
Racing tracks. When you see this Formula One Grand Prix, these cars are moving at very high speeds and they are turning on this circular tracks. Motography, where these motorbikes are turning on this tracks. If you have seen Olympics or otherwise cycling, and they are turning on the circular tracks. In Olympics, they have this circular track and something like that as well. And these cycles are moving on that circular track. They are turning. How does the car turn? So how does the cycle turn? You will say, sir, what is this? It's simple. Move the steering wheel and turns. No, the steering wheel doesn't turn it. This question is similar to what I discussed in one point in time, that there was a question in Y voice, a very popular question: what makes the car move? It's not the engine that makes the car move, it only gives you the power. The only way the car can move on road is by friction between the tires and the road. If there is no friction, the tire will keep on rotating, nothing will happen, car will not move at all, whether it's a Ferrari or a Lamborghini. It will not turn, it will not move, it just keep on rotating. Friction is what makes it works. That is why roads, even if they look very smooth, they have a lot of friction. These Formula One tracks, they have a lot of friction. And why? First, it will make the car move. Second, it will make the car to turn. How can a vehicle turn? Now, there are only two ways in which the vehicle turns on a circular track, or any vehicle changes direction. The only way a vehicle can change direction is by two ways. What are the two ways? The first way is by using our friendly neighborhood. Smart Spider-Man. By using our friendly neighborhood, friction. Friction is our Spider-Man. by using friction only. By using friction only. What is this? How can friction help turn a car? To illustrate this, let us draw a vehicle turning on a circular track. And to understand this, what I'll do, I'll first draw a road. Now this is what you call the front view of the road. This is, let us say, the center of the circular track, and this is my car. Now my drawing is not very exceptional. This is the back side of the car. It doesn't look like a car, but for argument's sake, let us take it for a car. Now this car is turning like this, so it is moving inside. I hope you understand this is horizontal circular motion. I cannot draw this horizontal circular motion on this sheet because I have to make the vertical direction like this. If I draw it like this, you will see, sir, this is vertical circle. So I don't want to draw a horizontal circle as a vertical circle. That is why this car is trying to turn. And this car is trying to turn, and the radius of this circular track, remember, I told you any curve is a part of a circle. The radius of the circular track is r. It has to turn. It's a graphy race, and there is a circular track, and it has to turn. Voila! How will it turn? Now steering wheels, the wheel doesn't turn it. What turns it? Let me draw the free body diagram and understand what turns it. Vehicle has got its weight, mg. It always goes down. Nothing can change it. Then there is normal reaction coming from road, n. And you will understand this normal reaction will be coming from ground. Now I have to make three equations. Now this normal reaction is going upwards, weight is downwards. Now this normal reaction or weight cannot give it the centripetal force. Who is going to come to save it? Who is going to make to turn it? Who? And it's a friendly neighbor, friction. Friction will come to the rescue. Now the question is, which type of friction will come to rescue? Which type of friction will provide it with the centripetal force? Remember, we know two types of friction. I'm doing the same thing with... Yes?
Kinetic friction.
Kinetic friction comes the answer, and the answer is wrong. Kinetic friction cannot make it turn, beta. When a car is slipping, you can't turn it. That's how accidents happen. When the car slips, you just go away. Nothing can stop a slipping car. No brakes. Only God, or a wall, or a truck, where it goes and bangs. Nothing can stop a sliding thing. Not in this universe. So kinetic friction will only come when it slides. And when a car slides, or when a bike slides, bye-bye. Static kinetic friction doesn't help, bacha. Then which friction comes to the rescue? There's only one friction that comes to a rescue, and which is?
Static friction.
Static friction. The tire has to turn. When the tire turns, then only brakes work. If the tire slides, brake doesn't do anything. Car will keep on sliding. Why will the car stop? Brakes cannot stop a sliding car, bacha. Only when the vehicle, the tires are rotating, can the brakes work. Sliding brake doesn't work. So you don't want your vehicle to slide. You want your vehicle, the tires to keep rotating, then only you can stop it. If it starts to slide, that you might have seen ice road truckers. Have you seen that documentary? Ice road truckers on Discovery. Big trucks moving on ice. Alaska and all these places in America and Canada. Then they put all sorts of chain on their tires so that these tires don't slide. If they slide, only God can help them. Even God will not come. Because even God cannot fight kinetic friction. You'll have to put in something in the way so that it bangs there and it slides. So the only friction that is going to stop it or provide it the turning force is static friction, and pray to God that kinetic friction doesn't come, because if kinetic friction comes, then none will not be able to stop it. We keep on sliding. Kinetic friction is always less than static. Remember that. Static friction can keep on increasing. Kinetic does not.
Yes, sir.
Don't want your car to slide. Nah? Because you know when your bike slides, you fall. When the tires are rotating, you don't fall. When the bike slides, you will fall.
Yes, sir.
Static friction is the friction that is going to help it. Now we are going to draw. We are going to write the three equations that we know. What is the first equation? The first equation is in the tangential direction. In the tangential direction, nothing is happening. No force. The force in the tangential direction is 0. Do you all understand this? Can I have some reason that you understand this?
Yes, sir.
The second equation is in the radial direction. What is the second equation? Can anyone tell me that? This second equation is in the radial or the centripetal direction. What is that equation looking like?
Centripetal force.
F centripetal would be equal to always, without any doubt, it will be equal to
M
m.
omega square capital.
There is no omega. It is not. We are not taking it as circular motion. We are taking it as a
V square by capital R, sir.
mv square by capital R. And you must also realize who is giving this centripetal force. Friendly neighbor. Static friction. Fs. S standing for Spider-Man or S standing for static friction. Both are doing the same job. Friendly neighborhood. What about the third equation? Which is in the perpendicular direction.
Tangential, sir.
It's not tangential, it's the perpendicular direction. There cannot be any motion in the perpendicular direction, and hence the equation is very simply upward should be equal to downward. So what is the equation? What is the equation in the perpendicular direction? No one knows it. N is equal to mg.
mg, sir.
Yes, but that is the equation in the perpendicular direction. N is equal to mg. Simple as that. Beautiful as that. Now we have three equations and we are done with our force dynamics thing. Now we have to go back in the past and take out something from that past and then use it. What are those things that we have to take from the past so that I can solve this question? Anyone? Going to past, taking something back and solving this question. What I am going to take back from the past? No one knows it. F static is always less than or equal to F limiting, which is always equal to mu s, where s is the value of static coefficient of static friction into n. Do we all remember this? Yes or no? I now just need to put the values of everything. F static is m v squared by r is always less than or equal to is always less than or equal to what? Mu s into n. Yes or no? Do we understand this? Do we understand this?
Sure.
I'll put the value of n as mg. So I'll get the equation as mv squared by r will be less than or equal to mu s multiplied by mg. M say m will get cancelled. And we will get the value of v is less than or equal to root over mu s into r into g. So the value of v must be less than or maximum. It can be equal to the root of mu s into r into g. Do we understand this? Can I have some reason that we understand this? Yes. That means whenever you are turning on a circular track, should you turn with a very high speed or should you turn with a less speed? What should be your criteria when you want to turn on a circular track? Should you increase the speed? Let me increase my speed. Or should you go slow, slow, slow? No, let me keep the speed low. What is a better option? More speed or less speed?
Low speed, sir.
Why there is less speed? Because your speed must be less than a particular value. If it becomes more than this value, what will happen? If it is more than this value, what will happen? More than a certain value, what will happen?
Lights off, sir.
Yes, the car begins to slide. When the car slides, brakes don't do anything. You put all the brakes, nothing will happen. You put the gear on, nothing will happen. Because that will only stop the vehicle to stop rotating. The vehicle is not rotating, vehicle is slipping. And the only thing is kinetic friction, and you hope that kinetic friction is good enough to stop you. Because your car cannot stop on its own. Brakes are gone, gear is gone, everything is gone. So you can only turn with the maximum possible speed using some common sense. Can you tell me what is this maximum speed that I can turn the car on this road? What is my V max here? Can anyone tell me what is my V max here? Can anyone tell me what is my V max here? What is my V max? The maximum value of speed that is possible that I can turn this car on this road using friction only. And even tell me what is the value of V max, the maximum possible speed which I can turn this car so that it does not sleep and I have a good ride.
Mu s
Good.
RG.
Yes, the maximum possible speed is mu s RG. And that is why whenever you are moving on a highway and there is a turn with all these traffic signs, signals, turn ahead, blind turn ahead, Falana and Dimaka, they will also give you the maximum speed. Okay, this is the maximum speed. Don't go more than speed. Otherwise, your vehicle will not turn and you will bang somewhere. Am I clear with this? Can I have some reason that we understand this?
Yes, sir.
Give you a minute to finish. I'll have to wind up this chapter here today. One more thing is left. We'll wind it up here. A minute, only a minute, 2 minutes. Well, I hope everyone has noted this down. Yes or no?
Sir.
Yes, sir. Then, sir, comes the next and the last thing for this particular topic. Again, I'm going to turn, but now I'm not relying on friction. I don't want angle. What angle? Which angle are you talking about? Tell
Some
me.
angle, sir.
I turn at some angle. How do I turn? I am on a bike. Probably I can turn at an angle. If I'm in a car, how do I turn at an angle? I am driving a car. Ooh, must. How do I turn at an angle? Do I make myself ooh like this? That makes me turn at an angle? Does that work? What angle are you talking about? Yes, there's an angle. Which angle are you talking about? That is the main question. Which angle?
Banking angle.
Banking angle. Yes, banking of roads. Banking of roads. So you have heard about it? What is banking of roads? So instead of the road being flat like this, I make it at a very small angle, and you might have seen this. Highways, all these car tracks are like this. They make it at an angle. We call that angle, let us say, as theta. Now, when your vehicle is like this, here, again, I'm drawing the back side of the vehicle. The vehicle is going inside. Now, this is the radius of the circle on which your vehicle is turning. This is your capital R, the radius of the circle on which your vehicle is turning. Now, what happens when you make the angle like this? If I draw the free body diagram, My n comes, oh, why does my n come here? My weight mg comes here. My normal reaction n goes here. But now, no, n does not go here. Why I'm throwing n here? I've gone mad. My normal reaction comes like this. It is always perpendicular. It is always perpendicular. Now I can resolve this normal reaction into two components. One is here and the other one is here. Can you tell me which one is the red one and which one is the green one? I leave it to you to understand this. If this angle is theta, this angle will also turn out to be theta, and hence this component becomes n. Why am I making so much mistakes? This component becomes n cos theta, and the green component
n sin theta, sir.
yes, this component becomes n sin theta. And again, I write the three equations. What is the first equation in the tangential direction? Is there any force in the tangential direction? Come on, be fast. Is there any force in the tangential direction?
0, sir.
0. Well done. That takes me to the second step, the green equation. What is the green equation? Tell me what. FC is equal to m v squared by capital R. Do we all understand this? Can I have some reason that we understand this?
Yes, sir.
That must be equal to, who is going to give it the centripetal force? N sin theta. Do we understand this? Yes or no? Then that comes the third equation. The F perpendicular has to be 0. Forces must balance out each other. That gives me a very simple.
Equals to mg.
Yes, n cos theta will be equal to mg. This is the third equation. This is the second equation. You can simply divide them and get me the value of v. Small task. You are good enough to do this task, so I'll not take any much time and I'll just write the value of v. V will be equal to 1 second, 5 seconds. Can anyone tell me what is v? Root over what? V is root over what? No answers. Disappointed, but I have to move on in life. It is R G tan theta. Do we all get this answer? Yes or no? Please raise your hands. GR tan theta.
Sure.
Yes. And that is the maximum speed possible for only banking. So, how do roads are made in general? They don't rely on friction only. They don't rely on banking only. If it is a high-speed road, expressway, many expressways are coming up these days. They use both. They bank the road as well, and they make it very rough when it is turning on a circular track. So they use both banking as well as friction. That has to be a third topic, but I'll not cover it here now. We'll probably do it once your 11th standard is complete and we get a small gap between 11th and 12th. That is when I will be doing this banking as well as friction together. Right now we just take them separately. One is purely friction, the other is purely banking. And if you can look with your eyes closed, even you can see the relation between them. If you can remember any one of these, you should be able to remember the second one because they are very closely related to each other. See, open your eyes and see.
Sure.
Open your eyes and see. Yes, see.
Tan theta.
Yes, instead of tan theta, you have mu s, and tan theta and mu s are also related to each other. If you remember that angle of repose,
Okay.
angle of repose, angle at which it starts to turn, it starts to move. Mu s is tan theta. Remember that?
Yes, sir.
So, when that tan theta and this tan theta are different, but you can relate tan theta with mu s. Mu s is tan theta, and you have your answers. Do we get this? Can I have some reason that we understand this, sir? Easier to remember one if you remember the second one. Now this banking of roads, even if you are on a bike, you can use this banking and turn. But if you are on a bike, cycle as well. And you might have seen this motography. I mean, I don't know how much of you, how many of you are a fan of motography, but in my time, motography was a big thing, and I used to watch a lot of motorcycle race. And when you see these motorcyclists, all these safety gears, all these pads, and this and helmet, and and they turn at very fast speeds. You might have seen it in Hollywood movies. And while they're turning, they do something. You can call it a stunt. How do they turn? The
They will
vehicles,
bend, sir.
they'll bend like this. Now, I can't bend the car like this.
Yes, sir.
Yeah, but in Rohit Shetty movies, I mean, even the car can run on two vehicles, on two wheels. But in reality, it does not work. But I can always do this. I can always turn myself when I am on a bike, and that will help me in turning. How does it help? I'll just give you. I'll not explain it further. Oops, what happened? Where did this go? What I'll do is I'll just try to explain it, and the answer is similar. Now see, how does this bike is able to turn? Now this is the road, the same road as before. Now this is the bike. This is the cyclist. If he is straight like this, nothing helps him. But if it turns here like this, voila, something happens. If it turns himself like this, what happens? His weight is still downwards. Oops, the red color should be here. The weight is still downwards when he's bending like this. The weight is still downwards, but his normal reaction goes in this direction. Do we understand this? Yes or no? When he's straight, his normal reaction is upwards. But when he bends like this, his normal reaction goes this way. Now, when his normal reaction goes this way, then something happens. It can be resolved into two components. This component, which is n sine theta, if I call this angle as theta, and the upper wala component, let me call it a red as n cos theta. It has become blue only. This becomes n cos theta. So when he bends, what happens? He's resolving his normal component into two components. N cos theta balances his weight. N cos theta balances his weight, and n sine theta gives him the centripetal force. So instead of banking the road, he relies on his own banking. So he's banking himself. By bending over, he's banking himself. And then if you solve this equation similar to the equation that we have solved in banking, you will again arrive at the same result. What is the speed that is possible if he does this stunt? What is the maximum speed that he can turn his vehicle? And the answer would again be same. It will be equal to rg tan theta. Do we understand this? Yes or no? Can I have some reason that we understand this?
Yes, sir.
And that is why you see in this motography, they are turning at very high speeds, and they literally lie on ground. They literally lie on ground. Because more the angle, more the value of theta, more is the value of tan theta. If tan theta is 45, theta is 45, tan theta becomes 1. If it is more than 45, it is 60 degrees, it becomes root 3 by 2. Oh, voila. Now, it becomes root 3. Tan 60 is root 3. And if they bend at 90 degrees, which is not possible because they will just lie on flat on ground, he can have an infinite speed of turning, and that is impossible. So they cannot make it at 90 degrees because they will just fall flat on ground. But the more the angle, the more is the speed that we can turn. You cannot make a banking road of 90 degrees. I mean, everyone will fall down instead of turning. So that is impractical design. Normally, the angle of banking is 2 or 3 degrees. Sometimes in place of banking, and please note this down because you might have this. Sometimes instead of giving you the banking angle, what they give is this thing. They give you the height, how much the vehicle is, how much the road is raised, and they give you the length of this road, L. So if you are
There must
given
be some angle now, sir. Banking angle. More than that, if we bend, it slips, right, sir?
yes. If that theta is more than mu, if this theta is more than your mu s ka tan theta, if the tan theta is more than mu s, it will just slip down. And that is the reason that you have both banking and friction coming in. So sometimes instead of giving you this angle theta, this is normally 2 or 3 degrees, not more than that, beta. They don't want you to slip like this. Instead of giving you theta, they might give you h, or L. Then you can find out the value of this theta. This tan of theta will be equal to H by L. Is everyone getting this? Can I have some raised hands that we understand this, sir?
Yes, sir.
Now, if this angle is very small, this tan theta is also equal to your sine theta. So sometimes instead of giving you this L, they can give you this L. Now, even if you give you this L, this angle is very small. So even then you can do H by L. You will get the value of sine theta, but that sine theta will be equal to tan theta. Is everyone getting my point?
Sure.
The angle is very, very, very small. They can't bang a road at 10 degrees, but they do it. In case of cyclists, you have seen this this cycle race on Olympic tracks. They bang it very high because they want cyclists to turn at high speeds, and they know that cycles will not fall down. Have you seen the cycle race in Olympics? The banking is high. The banking is just like a death well, more like a death well rather than cycle race. On that note, I've taken 4 minutes extra for today, but I had to finish this thing up. I'll say goodbye for now. I hope you have liked this class and understood the horizontal circular motion. There is nothing that is left in this horizontal circular motion that you don't know now, and I can guarantee you that on a stamp paper. We'll start with vertical circular motion in the next class. The class is dismissed. Enjoy your day. Go to your next class. Stay safe and come back in the next one, and we'll have more fun. Take care. Have a nice day. Stay safe, beta. Get vaccinated. Bye bye.